In this video, I'll be walking through a demonstration of the sampling distribution of the sample mean in order to illustrate how a sample mean is itself a random variable, as its value will vary from sample to sample, and how we can construct the probability distribution of the possible values that the sample mean can take. The example I'll be using is the number of siblings for U.S. residents, and what I have here is the probability distribution for the number of siblings based upon data collected by the U.S. Census Bureau. So you can see I have that data in the data table and then an associated probability histogram here. You can see that the distribution is fairly skewed to the right, with a mean illustrated here in red of about 1.55 siblings. So it's very common to have 0, 1, or 2 siblings, and not as common to have 3 or more siblings. Alright, so to illustrate the sampling distribution, I'm going to use the applet function in this statistical software package here, which is known as StatCrunch. I'll go to applets, and then I'll come down to sampling distributions. And then I'm going to be constructing the sampling distribution based on the siblings data. And then let's make this bigger. Alright, so what's going on this screen is this first graph represents the population data. And it's kind of spread out, doesn't look exactly like the histogram we just saw because it's just using smaller bin widths. This next graph is going to represent the different samples that I'm going to take from this population. And the final graph will be plotting the means from each of the samples that we take. Let's first see what happens if we take samples of size 5 and then compute the mean from each sample. Alright, so let's sample 5 people from the population. So it looks like the first person had 1 sibling, then 0 siblings, then 1, and then 3, and then 3. So that was my first sample. The mean in this sample of 5 people is 1.6. So the mean number of siblings by the 5 people in my first sample is 1.6. And then that value 1.6 becomes the first observation in my distribution of sample means. And so the sampling distribution is going to look at what would the distribution of sample means be if we were to repeatedly sample over and over from the population in order to get an idea of how far away you can expect your sample mean to be from your population mean. Alright, so that was sample number 1. Let's take a second sample of 5 individuals. So this first individual had 0 siblings, then 0 siblings, then 1 sibling, then 0 siblings, and then we have 3 siblings. So that mean is much smaller. So my second sample only had a mean of 0.8. And that becomes my second observation in the distribution of sample means. So again, we see that even though we're sampling from the same population, the mean from one sample to the next isn't necessarily going to be exactly the same, but they're probably going to be pretty close, and they're going to be pretty close to what we're trying to estimate, which is the population mean. Alright, let's take a third sample. Alright, so we've got 2 siblings, and then 4 siblings, and then 0 siblings, and then 1 sibling, and then 5 siblings. We had a lot of variation in that sample. Had a very high mean, a mean of 2.4. So that becomes the third observation in my distribution of sample means. Alright, now I could keep doing this one sample at a time, plotting the mean from each of these samples, and continue on and on and on, except this applet has a handy 1000 times button, and if I hit that, it'll start taking 1,000 different samples and plotting the means from each of these samples in my distribution of sample means. So let's do that. Alright, so there's 1,000 samples of size 5, there's another 1,000 samples of size 5, and I can keep going and going and going to really get our distribution of sample means nice and filled in. Alright, so here I've got about 30,000 different samples of size 5, and the means of each of these samples is plotted here. Again, there's a little gap just because of the bin width, but if you could imagine drawing a smooth curve over this, you would see that, like the population, this distribution for sample means is a little skewed to the right. However, there's not nearly as much variability in our sample means as there were in just the individual observations, right? Because with individual observations, it was possible to have 6 or 7 or 8 siblings, but we see it's not possible to have means that high. And that's reflected in the standard deviation values here. You can see the standard deviation in the population was 1.5. So a typical distance from the mean for the population is 1.5, but a typical distance for the distribution of sample means from the mean of the distribution is 0.67, so much smaller. Also, one very interesting phenomenon is the fact that in the population, the mean number of siblings is here at, or that's the median, the mean number of siblings is here at 1.55. And then you can see in our distribution of sample means that the mean is also about 1.55. So this is kind of a hard concept, that we're taking a bunch of different samples, plotting the mean from each of these samples, and then when we calculate the mean of all those means, it's equal to the mean in the original population. So that's a lot of means that we're talking about. So here you can think of the average of all the averages is equal to what we're trying to estimate, which is the population average. And our sample means are going to fall closer to this population average than our individual observations. Okay, so this illustrates what the sampling distribution would look like for samples of size 5. The next question is, what can we expect if we were to take larger samples, let's say of 30 people at a time? Alright, so I can take one sample. So here's a sample of 30. It had a mean of 1.13, and that becomes the first observation in my distribution of samples. Then I can take a second sample of 30. It has a sample mean of 1.7667. That becomes the next observation in my distribution of sample means. And I could keep doing this one at a time, but why would I do that when I have the 1000 at a time button? So now we can see right off the bat that there's not nearly as much variability in the sample means from samples of size 30 as there is in the population, and as there was when we were looking at samples of size 5. So this tells us that when we take larger samples, we can expect the mean of these samples to typically be closer to the population mean than we can with smaller samples. And again, you'll notice that the mean of all my sample means is equal to the population mean of 1.55. And you'll also notice that when we have this larger sample size, now I would describe this distribution as being fairly symmetric, as opposed to with smaller samples, it was still pretty skewed to the right. Now things seem to fall around the population mean in a bell-shaped distribution. Alright, so that illustrates what you can expect for your distribution of sample means when you're starting with a population which is skewed to the right. But what if we had a population which was instead already normally distributed? What can we expect? So let's go back to our sampling distributions applet. This time select a normal population, and we'll leave the mean and standard deviation at the default here of 25 and 5. So now here I'm starting with a population which is normally distributed. Let's see what happens when we take samples of size 5 from this population. Okay, here's my first sample. We see that it has a mean of 22.7, and that becomes the first observation in my distribution of sample means. Let's take a second sample of size 5. Now I have a second sample mean added to my distribution of sample means. And let's go ahead and skip to the answer. Okay, so again we see that the average of all the averages is right at the population average of 25. But when we start with a normal population, our sampling distribution looks approximately normal, even when we had the smaller sample. So that's a difference between what we saw when we were starting with a skewed right population. All right, well, what happens when we take samples of size 30? I could take these samples one at a time. Here I have a mean of 25, which gets added to the distribution of sample means. And then I could add 1,000 different sample means to my distribution. And again, it's going to look approximately normal. The mean is going to be equal to the population mean. Okay, so the mean of all my sample means is equal to the population mean. And again, we see that our standard deviation has decreased yet again from where it was before to what it is now. So this illustrates several properties of the sampling distribution of sample means.